Let's notice this. Calculate the bond dissociation enthalpy of phosphorus chlorine bond from the given data, that is delta H of formation of PCl3, formation of Cl. Usually the formation part should always be given in standard values. So that is a standard value only. And atomization of phosphorus is given. In such case, how do we solve it? Notice this. What I could do here, first write the equations, just like how I told you earlier. So P solid, see, normally phosphorus exists as P4, but take the hint from the atomization. He didn't give it he didn't give the data for P4, he simply gave it as P. So take that into consideration as the standard form. So P plus 3 by 2 Cl2 gas, that should give PCl3 gas. Yeah. For this, the delta H value atomization is 306. Second equation, formation of chlorine. Cl2, half of it becoming Cl gas. This is the delta H of formation, which is given as 121. Next one, atomization. P solid converting into P gas. That delta H of atomization is given as 314. This is the data given to us, and we need to calculate epsilon PCl. If I write this in terms of epsilon values, remember, for writing everything in bond dissociation enthalpies, you have to write everything in gaseous state first. Now, first I need to make sure that this P solid is converted into gaseous form. That means I'm supposed to add this extra value to that. So, delta H of atomization plus 3 by 2 times of epsilon Cl and Cl. This is the reactants energies minus product energies. See, in product we have phosphorus with 3 chlorine groups, right? So which means it is supposed to be 3 times of epsilon P and Cl bond. Yeah. And that is equal to delta H value, which is given as 306. Atomization is given. And what about epsilon here? You notice that for half a mole of this one, which means half of epsilon Cl and Cl, the energy given is 121. So epsilon of Cl will be equal to 242. So we got all the data now. Atomization is 314 plus 3 by 2 times of 2 times of 121, because 242 I can write it that way, minus 3 times of x, which is what I need to calculate, that is equal to 306. So 3x is equal to 314 plus 3 times of 121, which I will write it as 363. Okay. So from here I'll get x is equal to how much we are getting, 677 by 3. Okay. So which is 2 and 2 and 17 is approximately 8. Okay. So 228 is the epsilon of PCl approximately. Got it? Let me see if at all I have taken everything correctly. Formation, yeah, data is correct. We check out with the answer key also. Any doubt here? Okay. Now, the next topic what we will discuss is about resonance energy. Okay. See, resonance energy, what are the basic terms we need to know is that it is always a negative value. Resonance energy is always negative value, which means it is a released energy. Second, it is a stabilizing energy. More the energy release, that means more is the negative value, more is the stability. Okay. And resonance energy, it defined in many ways. One is delta H of formation experimental minus delta H of formation theoretical. Delta H of combustion theoretical minus delta H of combustion experimental. Delta H of hydration theoretical minus delta H of hydration. Sorry, here also it is hydration. Hydration experimental. Okay. This is the way it has been defined. Clear? Now, to put it in a perspective, like what exactly it meant. Okay. So normally, let me, before going into the question, let me explain you that terminology here once. Okay. I'll just push down this question. Yeah. Check this part here. Suppose if you have, uh, uh, any X here, let me put this as X here. Any X here, which is a resonating structure. Got it? And that form is converting into a normal structure. Correct? That form is converting into a normal structure, which means energy of this normal minus energy of this resonating structure. Correct? That should be the delta H here. So delta H of the reaction is equal to delta H formation of the normal Xn minus delta H of formation of XR resonating structure. Okay, got it? So obviously, if at all you notice the energy wise difference here, so delta H of the resonance energy should be negative. Okay, so negative means they should have less energy and they should have more energy. Is that clear? Okay, typically that should have to be negative here. For example, what I'm trying to say is when I say resonance energy, I meant this one, benzene, and here normal structure means, sorry, yeah, normal structure is like this, and a resonating structure is like this. Got it? Clear? Normal as a hybrid structure. Okay, right. Now imagine, suppose if at all I am making a reaction wherein an element A has a resonating structure here, and from here you are going towards an element B, which is also a resonating structure. That means we are writing a resonating structure here. So in that case, I can say that from this resonating structure, first I need to convert that into a normal structure. And from there, I have to convert everything into atoms, atomic form I have to get. And from there, I have to combine all of them so that I can get a normal B structure. And from B, again, I have to go to that resonating structure. This is a typical uh, bifurcation of the energies. So here, from normal to sorry, for from resonant structure to uh, normal structure, the energy that is released is the resonance energy. This is the energy release, which is resonance energy. It has to be negative. Got it? This is negative energy. Clear, beta? Next, here because you have to break the bond, energy delta H will be positive. Here, these are all bond enthalpies. Bond enthalpies that has to be positive. Correct? And here delta H will be negative because bonds are being made. Okay. So from the atomic form, bonds has been made here. And from here to here, again, energy is minus of resonance energy of, B in this case, minus of resonance energy of B. So you got to always think in these lines whenever you are trying to break, molecule into various forms. Everybody clear? So any given question, you try to always do this form. So let me show you with some example here. Okay, very simple example. For example, carbon solid plus O2 gas, it is converting into CO2. CO2 will also have a resonating structure. Okay, and normally you have been given here as a resonating structure R. Okay, so if it is given as resonating structure R, that means what do we need to do here? First, I need to convert this carbon solid into carbon gas. Then I need to convert oxygen into 2 moles of oxygen gas. Correct? Then I need to combine these two so that it can become carbon dioxide, which is normal. Okay, this is normal form. Okay, from the normal form, I need to get that into a resonating structure. Got it? So what are the energies that has been used here? Check out. First, here delta H of atomization is required. Here epsilon of O double bond O is required. And thereafter carbon and oxygen has been combined. So I can say there is bond dissociation energy of carbon and oxygen, right? Because here, if it is a normal bond, that means it should be O double bond C double bond O. This is the bond we should have. Correct? Is this point clear, beta? So that means I have to break these two bonds, but I'm making it. So that means negative of 2 times of delta H naught of C double bond O. Sorry, epsilon of C double bond O. Okay. And from here, this is from the normal form towards a resonating form. Okay. Sorry, I meant here I made a mistake here. Resonating structure as in this one. This is the hybrid form. Normal as in this form. That's a mistake I made. Yeah. Okay. One second. So formation of products are correct. Okay. Here from this resonating form, if at all I have to get this here, sorry, made a mistake here. It should be positive. Okay. And here this need to be positive, but the resonance energy is always about normal form means this one, that is canonical form, and this one is a hybrid form. So go back to the uh, resonance energy form. Here you can see normal form means this one, isn't it? Correct. And hybrid form means this one. This is the hybrid form. Experimentally whatever you find is the hybrid. In terms of benzene thing, if at all I show you, experimentally what you will find is for actual benzene. Theoretically you can only find it for its canonical structure. Understood now? Okay. So this is the form I'm talking about. So in case if at all I have to get the formation of resonance energy has to be the formation of the experimental value, which is resonating structure, minus the normal value. Okay. So I made this mistake here. It should be N here and R here. Now it's all okay. So and here R and N. R and N. Okay. This one. This is the form I need to write. Check. Okay. Please check again. Got it? Here resonating structure as in canonical structure. Okay. Okay. Now this has to be negative value. Coming to the same point here, you can see this is the normal form. Okay. And resonating structure, I mean, the one which is having an hybrid form here, it could be like this. C, oxygen, oxygen, and this double bond is moving. So we cannot exactly figure out what is its structure. We can only say hybrid form is present. So to get that hybrid form, what I should do? I'll have to spend some resonance energy out. Got it? This is what theoretically appears like. If I write in terms of values, it will become much more easier and clearer to understand. Check out how we can solve this question now. Check. For example, if I need to find resonance energy of N2O, okay, let me show you what is the structure of N2O. N double bond N double bond O. This is one resonating structure. The other resonating structure is N triple bond N. This is plus and minus, and N single bond O plus. These two are the resonating structures, and its hybrid structure will be like this: oxygen with double bond here, and here one bond is moving like this. Positive charge is always here, delta negative and delta negative. So this is called the hybrid structure, and this is called the canonical structure. So there are two canonical structure and one hybrid structure. Now this is where you have to put your intelligence, that out of these two canonical structures, which structure is more relevant to the given data. That is one very important task. See, there are two structures we can have, correct? But which data is given in the question? Did you see any of the data having N triple bond N? Yes, it is there. Did you see N single bond O? Is there any data given? No, it is not given. Correct. But if you see here, N double bond N data is given. Yes, it is given. N double bond O data is given. Yes, given. So now tell me which one of the canonical you will consider for solving. First one and not second one. Got it? Guys, understood? So first you got to decide which of the canonical you need to use for the question. Okay? Now, one thing is sorted. Now check out what we have to do. First, to write the resonating structure of N2O, okay? Theoretically, if I want to get this structure, this is a theoretical way of doing it, because experimentally we don't know what is the data. So first we'll figure out what is the theoretical data. Theoretically, to get N2O, theoretically to solve uh, delta H of formation of N2O, then what is that you will use? You will use 1 mole of N2 gas plus half a mole of O2 gas. That should give us N2O gas. And N2O gas as in, what is the structure I am expecting? N double bond N and double bond O with plus minus. This is the structure I am expecting. So this is a theoretical energies which you have to put it through. Now check what is the data given. Okay. Delta H of the formation. This is about delta H of formation of N2O theoretical. This is theoretical value. So delta H of formation N2O theoretical value will be equal to epsilon of N triple bond N, because you have to take reactants energy minus products energy, plus half into epsilon of O double bond O. This is the reactants energy minus products energy. Product we have epsilon of N double bond N plus epsilon of N double bond O. This is what is there in the product. Everybody clear what I have written? Now let us put the data whatever that is been given. Epsilon of N triple bond N 946 given, plus half into epsilon of O double bond O 498 given. That minus epsilon of N double bond N double bond N 418 given, plus epsilon of N double bond O 607 given. Done. These are the values which has been given here. Okay. So now let me calculate and see how much we are getting. Okay. 946 plus 0.5 into 498 minus 418 minus 607. I am getting as 170. This is the delta H of formation of N2O, everybody. Okay, and all the energies are in kilojoules per mole. I have not written that, but yeah, it is kilojoules per mole. It is all written. Okay, now we got delta H of formation theoretical value. That is the first thing we got. Experimental value is given to us. Experimentally, how much is the value given? 82. Theoretical value we got. Now I need to find out what is the resonance energy. That is a question mark as well. So how much is the resonance energy now? Resonance energy will be equal to delta H of formation of N2O experimental minus delta H of formation of N2O theoretical. Okay. So experimentally how much we have got? 82. Theoretically how much we got? 170. Clear? So how much are we getting here? So 88. Okay. Clear beta? Everyone. Right. So 88 kilojoules per mole with a negative sign. So that would be the amount of energy which is released and which is called as resonance energy. Okay. Take a bit, take a minute, check carefully whether your thought process, the solution, everything is correctly matching or not.
Sir,
Yes, beta.
sir, how to choose that canonical structure?
Good challenge. Basically, whatever the compound is given, some idea you should have about structure, how it looks like. Otherwise, it becomes difficult. Okay.
Yes,
Mostly,
sir.
mostly what is the question that will be given? I'll tell you. Question will be like this: either benzene, this you can choose. This is the only thing you can choose. Okay. Next, you would be given something like a alternative double bonds. Correct. This is the canonical you have to choose. Now you can say, sir, I can have a resonating structure like this. Correct. But this is very less contributing. So you will not be considering this. You will only consider the structures which are sufficiently contributing. Within that sufficiently contributing, you can take one of them which is relevant to the question. Okay.
Okay,
If it
sir.
is carbon dioxide, you will take this as C double bond C double bond O. This is one structure. The other structure is O minus C triple bond O plus. Now, by chance, if the question's data is given as C triple bond O bond enthalpy, then you choose this one. Otherwise, you only choose this one. Okay.
Okay, sir.
Finished, everybody? Maybe you should try one more question. Hmm? Just to make sure you are, comfortable with this cases. Yeah. Right. We'll do two questions on the resonance now. Let's see this. Try this one out first. I'll give you a simple one first. All right. Calculate the calculate the magnitude of resonance energy of carbon dioxide. Okay. From data which is given in kilojoules per mole. Got it? Data given is epsilon C double bond O is 539. Epsilon O double bond O 498. Okay. Delta H of sublimation of carbon given as 780. Delta H of combustion of carbon solid given as minus 393. Okay. Hmm. Take a minute of time, see whether you are able to catch that up. These students, what we can say, I'll just give you one hint. You can go ahead after that. First, write the formation of carbon dioxide. CO2 is giving, I mean, C plus O2 is giving CO2 gas. Have you noticed that this is the delta H of formation of carbon dioxide, and that is same as delta H of combustion of carbon solid also. So actually, this data and this data is same. That's the hint you need to realize. Got it? Right. Knowing that hint now, on the reactant side, what I need to do? First, I need to convert everything into bond enthalpies. That means everything should be in the atomic form on the left hand side. So to get this into two atomic forms here, then here, what are the forms we will have? You know, uh, C plus 2O. If at all I have to convert this into the atomic form, okay, C gas plus 2 oxygen gas, correct? Then what I should do? First, you need to take this into a canonical form, okay? Canonical form. Canonical form is the most useful canonical form is carbon dioxide is C double bond O and double bond O. This is the form. Now notice what are all the energies that we are using. For doing this, I require delta H of sublimation. Here I require epsilon of O double bond O. Here I require 2 times of epsilon of C double bond O. Is that okay? Correct. This is the reactant side on the product side. So how do we write delta H of the combustion? Theoretical, because this is a theoretical value. Theoretical will be equal to, reactants energies minus product energies. Reactant energies are delta H of sublimation plus epsilon of O double bond O. This is reactant side minus product side is 2 times of epsilon C double bond O, which is equal to delta H naught of sublimation. Sublimation is 718 plus epsilon of O double bond O 498 minus 2 times of C double bond O. C double bond O is 539. Okay. So how much we are getting? This value I'm getting it as, I'm not sure. I'll just solve and see. 718 plus 498 minus 2 times of 539. So I'm getting this as 138. I'm getting this as 138. Okay. Now tell me what is what is the formula for resonance energy in terms of combustion? In terms of combustion, see, formation and combustion will go differently. Okay. When it comes to formation, if you go back here, formation is experimental minus theoretical. Combustion is theoretical minus experimental. Okay. So it is theoretical minus experimental. Delta H of combustion, theoretical minus delta H naught of combustion, okay, uh, experimental. But here is a quick problem. In most cases, correct, the combustion factor will always be, you know, inverse of the formation. Got it? Here, sign wise. Of course, combustion has to be negative. So whatever the answer that you are getting, it should be negative value. Is that clear? You guys understood what I'm saying? This value you should get it as negative. Understood? Okay. So theoretically, whatever you are getting a positive value. So that is incorrect, right? We should always get negative value. So make sure you insert that negative value here. Has to be negative. That is supposed to be negative here. Clear? Okay. But this is not coming out to be negative. For what reason it is not coming out to be negative? It is coming as positive. That means this entire value, correct? This entire value plus if at all I add resonance energy here, the resonance factor is dominant so much, correct, that it is making it as positive. Understood? Is that making sense? Clear? So that's why to get this part into negative value, because combustion theoretically also you should get it as negative value, but I'm getting a positive value, which means how much should have been the resonance energy? So the resonance energy has to be 138 plus, sorry, minus of, how much is this one? Minus 393. Minus 393. Add this, you'll get it as 531. Okay. That means this much amount of resonance energy must have been added here, sorry, subtracted here. Then only we should get it as negative value. Make sense? So therefore, resonance energy has to be, although it appears positive value here, it is actually how much? Minus 531. Okay. Chalo. If you are confused here, what I would suggest, since this is formation only, right? This one is a formation because combustion and formation would be same for this one. Correct? Combustion is normally written in terms of carbon and formation is written in terms of carbon dioxide. That's the difference. Clear, beta? So when you are writing this value minus 393, theoretically also, I mean experimentally, if this is a combustion, experimentally formation is also same value, minus 393. So if at all I write it this one, minus 393, then minus of, you know, minus of 138, that will come as minus 531. Okay. So that is resonance energy can also be written as delta H of formation of carbon dioxide, clear, minus delta H of formation of, I mean, formation of carbon dioxide, which is experimental, minus delta H of formation of carbon dioxide, which is theoretical. So here this is also theoretical value. So therefore use this one. Here you will get this as minus 393 minus of 138. So that is coming as 531. Okay. So when it comes to combustion, you need to be careful about the sign because it is supposed to be negative value, but you are getting as positive value, which means the resonance value has to be highly dominant factor in this case. Please go through it once. Check if you have a doubt. Let me know. Finished? Ciao. Let me just add one more question and then we'll go ahead. Guys, let's try this one also. To in fact explain this question, first I need to give one more definition. So I'll give that first. Okay, what is uh, heat of hydrogenation? Heat of hydrogenation. Delta H naught of HYD. Hydrogenation or enthalpy of hydrogenation. Heat of hydrogenation you can say, or enthalpy of hydrogenation. Yeah. Let's see. Suppose if at all I have any double bond and I'm adding an H2. Okay, I'm adding an H2, then it will convert into this H and H because you are breaking one pi bond and making these two sigma bonds. Energy is always released. Energy is always released, and this released energy is what we call it as delta H of hydrogenation. This is also called as delta H of hydrogenation. Okay. So this one is delta H of hydrogenation. Similarly, suppose if you have two double bonds here like this, I have a double bond here and a double bond here, correct? Then if at all I add H2, I require to add two H2 so that this is what it should become, alkane. Alkene should become alkane, right? So in that case, again energy is released, and this time the energy, this let me put this as Q1 here and Q2 here. That should be equal to delta H of hydrogenation. Again, it is defined as hydrogenation energy. But one thing you will notice that in 1 and 2, even when you compare experimentally also, even when you compare experimentally also, you will notice that experimentally, experimentally and theoretically. Theoretically means on paper, based on the data given, you are solving, that is theoretical. Experimental means you are actually making an experiment, then measuring the values. Experimentally and theoretically, values of delta H of hydrogenation would be same. In fact, delta H naught hydrogenation 1 will be, sorry, 2 times of that will be found to be delta H of hydrogenation 2, approximately almost the same value. Almost the same value you will find in both the cases. Clear beta? But if at all the structure is like this, the double bond are here like this. Now what happens? Here there is a resonance factor that will act. When you have an alternative pi bonds, there will be resonance happening. So this, if you add 2 moles of H2 to generate the alkane, same alkane here, then let's say this energy required in this case is Q3. Correct? Energy required is Q3. This has to be negative. And this Q3 is what we call it as delta H of hydrogenation 3. Okay. But now what you will notice, well, this is a negative value. Okay. Remember, this is a negative value. Now, if I compare the magnitude of them, that is delta H of hydrogenation of 2 will have a greater value than delta H of hydrogenation 3. Why the value didn't come same? Because earlier we learned that if at all I have one pi bond, let's say some 50 joules of energy is released. For two pi bonds, 100 joules should be released, and which was experimentally and theoretically proven. But when it comes to the same two pi bonds this time, instead of getting 100, now you're getting less than 100, maybe 90, maybe 80. Okay, clear? Okay, this value is definitely greater than delta H naught of hydrogenation 1, but it is less than this value. Because here also there are only two pi bonds, here also there are two pi bonds. Then why is that difference coming? The difference coming is because of the resonating structure. Okay, so that means this is an experimental value. If this is an experimental value, and then this one is a theoretical value. Sorry, delta H naught hydrogenation is a theoretical value. Then what I can say, theoretically I'm expecting this much amount of value, but experimentally I'm getting only this much amount of value. So delta H naught hydrogenation 3 is experimentally found value, while theoretically theoretically we expect same amount of heat released as delta H of hydrogenation 2. The same amount of energy should be released. That is what you are expecting, but it's not happening. Okay. Then how much is the lost energy? See, I can say that the lost energy, because both of them are negative values. Mind you, this is a negative value, this is a negative value. Which is a higher negative value? This one. And this is what? This is a theoretical value. So I can say that delta H naught of hydrogenation, theoretically how much you are supposed to get, that minus delta H naught of hydrogenation, practically or experimentally how much you are getting, that difference should be the resonance energy, and it should be negative. Okay, everybody please go through it once, check if you have understood what is resonance energy in terms of hydrogenation. Ah, yeah, clear on that? Samyak, did you get this beta? Samyak, is this clear?
Yes, sir.
So let's do the question now. Enthalpy of hydrogenation, enthalpy of hydrogenation, okay, of benzene is minus 51 kilocalories per mole. Okay, if enthalpy of enthalpy of hydrogenation of 1,4 cyclohexa diene and cyclohexene, sorry, 1 comma that much cyclohexene diene is minus 58 kilocalories per mole. Okay, what is what is resonance energy of resonance energy of benzene? Since we haven't done organic yet, I will just help you with the structure of it. 1,4-hexadiene means I have hexane with 1, 1, 2, 3, 4 here, double bond like this. This is 1, 4, 1, 4 cyclohexadiene. Right? Benzene structure, you know that. This one is benzene structure. Got it? Done. Now let's see this question, how to solve it. Realize this. What is delta H of hydrogenation for cyclohexadiene? That is, in case if you have this group plus 2 moles of H2, then it should become like this. Then the energy released, delta H of hydrogenation, is given as minus 58. Okay. Now I can say that for for two pi bonds, if this much amount of energy is released, for one pi bond, how much energy will be released? Okay. For one pi bond, okay, delta H of hydrogenation will be minus 58 by 2, which is minus 29. Minus 29 is what you expect for every one pi bond. How much energy should be released? This much amount of energy should be released, minus 29. Now coming to the benzene here, if I take benzene, then I require to add 3 moles of H2 to convert it to cyclohexane. Got it? Then delta H of hydrogenation, theoretically, how much do you expect? Everybody, theoretically, how much do you expect? It should be 3 times of this, correct? Because for one pi bond, if it is minus 29, for this should be 3 times of 29. This much amount of energy should be released. Everything is in kilocalories. At the end, I'll write down. Hmm? Clear, everybody? But for benzene, this much amount of energy should be released. Instead, how much is the hydrogenation given? Experimentally, how much was releasing? Only minus 51. So it is given that delta H of hydrogenation, okay, experimental for benzene, that is given as minus 51. Theoretically, how much is supposed to be released? This much is released. So resonance energy is equal to how much, beta? Theoretical minus experimental. So which is theoretical is minus 3 into 29 minus experimental minus 51. Done? Clear, everybody? So this will be the resonance energy, which is how much? Minus 36. Check, everyone. Did you get that? This much amount of kilocalories of energy should be released. Right? So I assume that you got some idea about how to do the questions based on resonance. Hmm? Right. The next type of enthalpy we'll be discussing is heat of neutralization. Heat of neutralization. Heat of neutralization supposed to mean that the amount that is released when 1 mole of acid I mean one equivalent of H plus ions and one equivalent of OH minus ions together, when they combine with each other, then how much amount of energy is released? That represents enthalpy of neutralization. Got it? That is enthalpy of neutralization. Okay. Now, as of now, since we didn't discuss much about enthalpy of, equivalence, so I'll not make you worry too much about that term. You put it this way, okay? If I take 1 mole of H2SO4, how much H plus will it give? 2 moles of H plus it will give. Agreed? Okay. So 2 moles of H plus will require 2 moles of OH minus to convert into water, isn't it? And you notice here, if I take 1 mole of HCl and 1 mole of NaOH, I'll get 1 mole of water, salt and water. Then the energy released is this much. Basically, here it is nothing to do with NaCl. It is to do with the water formation. That is, when H plus and OH minus, which are oppositely charged, when they connect and make a complete bond out of them, covalent bond, then the energy is released. Now you'll say, sir, what about NaCl? It is also making a bond. It is not making a bond. It is actually existing in aqueous ions only. So it is not actually making any bond between them. So there is no energy coming from NaCl. There is only energy released because of the water formation. Okay, clear? And since we don't have much idea about equivalents, I'll just give you a basic definition that is required here. Okay, equivalents, correct, of acid. If I'm talking about equivalents of acid, it means that how many number of moles of acid we have multiplied by the number of replaceable H plus ions. How many replaceable H plus ions we have? Similarly, equivalence of base is equal to how many moles of base we have multiplied by number of replaceable OH minus ions. Okay, this is what you need to learn. In the case of HCl and OH minus NaOH, you will see there is 1 mole and 1 equivalent, because it is only giving 1 H plus and 1 OH minus. So when these two equivalents combine with each other, the energy released is called as heat of neutralization or enthalpy of neutralization. Now in enthalpy of neutralization, it is always negative because energy is released when H plus and OH minus combines with each other. And what you would notice is, precisely if you do this at room temperature, around room temperature, the energy released is, exactly 57.1 kilojoules per mole or 13.7 kilocalories per mole. But very important thing is, here this is only valid for a strong acid and strong base. Strong acid and strong base means, see, HCl, the minute you add it to water, H plus and Cl minus will split on its own. It does not require any extra energy to do that. Okay. So any acids which split into their respective ions without taking any energy, then those are called strong acids. Like HCl, HBr, HI, H2SO4, HClO4. Okay, these are all strong acids. Anything which RCOOH, carboxylic acids, RCOOH, HF, okay, H2S, these are all weak acids. Okay, phosphoric acid, those are all weak acids. So check it out. If we take this as a strong acid, right? Now I'm taking as weak acid and strong base. This is a weak acid, imagine. This is a weak acid and this is a strong base. In that case, how do we need to check? If you have a weak acid here and trying to combine with the strong base, you will definitely get salt and water, no doubt about it. And the energy will also be released. And the energy released here is, let's say, delta H naught 1, or which you call it as delta H of neutralization of this case. And you know that HA is a weak acid, that means it will require some energy to break them apart. Okay, we require some energy to make sure H plus and H minus are separated out. That required energy, I'll call it as delta H2, which is also called as, dissociation energy, delta H of dissociation energy, because it is used to dissociate the H plus HA acid. And for NaOH, it is a strong base, so Na plus and OH minus, to separate them, you require no energy there. That's why I didn't write any energy there. Okay. So now what do we have here? We have H plus coming from HA, OH minus coming from NaOH. When these two combines, the energy which is released is delta H3, which is this should be same as delta H of neutralization standard. The naught here represents standard value. Okay. And this value is fixed. How much it is? Minus 57.1 in kilojoules or minus 13.6 in kilocalories. That value is fixed. Clear? Now notice this one. If at all I need to get this HA aqueous plus OH minus to give A minus and H2O. I have removed Na plus because Na plus is having no role here. In that case, how would I get this equation? To get this equation, first I should be able to remove this H plus and H plus from here. And then this HA plus OH minus to give water and A minus. I need to add these two equations, isn't it? I need to add these two equations. Clear? And that's what we do. So here, to get this equation here, HA aqueous, uh, sorry, I need to get this equation. I have to use these two. So what should I do? So I need to take this 2, correct? And then add with this 3 so that I can get this equation. Okay. 1 second, I made one mistake there. Ah, if I want to get this equation, let me write this. Yeah. How do we relate these three equations here? 1, 2, 3. Okay. So to relate these three equations, let me rewrite this part. Okay. What I can do, because this HA has to give into this H plus and A minus, this energy should be required first. And then from that required energy, once you get H plus and A minus here, and that's when I have to add OH minus so that this H plus can combine with this one and convert that into H2O. Correct? So what should I do here? I need to take 1, subtract 2 out of it so that I can get the equation 3. So what do I get? See, if I add 1 and 3 here, so I'll get this as HA aqueous minus HA aqueous, correct, on the reactant side, plus NaOH aqueous. This is all on the reactant side. On the product side, I have NaA aqueous plus H2O liquid minus H plus aqueous minus A minus aqueous. Okay. This is what we have. Clear, everybody? So now what we can say here, these two will get cancelled. These two will get cancelled. And this, if at all I write NaOH, instead of showing it as NaOH, I can simply write this as OH minus, because this is a strong base. So Na plus does not have any role as such. So this will give us much, easier way to understand. OH minus we have reacting. So we will get this equation. Now notice what are getting cancelled. You can see A minus will get cancelled. HA and HA will get cancelled. So what is left now? If I bring H plus on the left hand side, I'll get H plus OH minus aqueous. That is giving out H2O liquid. Yeah. So basically, I got equation number 3. But how did I get equation number 3? Equation number 3, I got it as after subtracting 1 after subtracting 2 from 1. So equation number 3 has what energy? Delta H of neutralization energy. And that is equal to delta H naught of neutralization 1 minus delta H of dissociation, which is 2. Got it? This is what we should have. And now let me me tell you, this I can write it in this particular form, the delta H naught of neutralization of strong acid plus strong base, because H plus and OH minus, if at all I'm not writing in terms of acid, I'm not writing in terms of weak acid, then this is for strong acid and strong base equation. That should be equal to delta H naught of neutralization, this is for weak acid and strong base combination, minus delta H of dissociation of weak acid. Yeah, correct. Please check it out, everybody. I hope you guys understood that what I have written. Finished? Right. See, I'll just show you with an example here. I have written that already. In this case, I'll just pull it up. Okay. You can see this is negative, negative, and positive. Okay. For example, if at all I have delta H naught of neutralization for strong acid like HCl and NaOH, this value is always given. Even if it is not given, you know what is the value that is to be taken. Okay, this is usually given in the question. If not, you should directly take this value by default. And now, if at all I tell you delta H of neutralization of acetic acid CH3COOH with NaOH, this value is given as, let's say, minus 50 kilojoules per mole. Then you can directly should be able to tell how much amount of energy was required to break CH3COOH into ions, respective ions. So that should be equal to minus 57.1 minus of minus 50. Okay, sorry, this whole should be taking this to the other side here. This should become positive and this should become negative. Okay, so which means uh, minus 50 minus of minus 57.1. So which is 7.1 kilojoules per mole. Then this has to be positive value always. Understood what I'm saying? Right. Now notice this, sometimes the delta H of dissociation value comes out to be negative, which sounds absurd. Like, you are to break a molecules, we require energy, but then how come it is coming negative? See, why it comes negative? If you take H plus and NaOH and you react this one, HF is a weak acid, NaOH is a strong base. But after combining, what you notice is that the delta H of neutralization for this value, for this equation, is greater than 13.7. It is supposed to come as 13.7, sorry, less than 13.7, but it is coming greater than 13.7. Now, this issue, that why it is coming greater than 13.7, it can only be understood considering that this HF, when you put it in aqueous form, it will get into H plus and F minus, okay, split out into H plus and F minus easily, where F minus is again surrounded by lot of water molecules, correct? And that lot of water molecules are the ones which is helping the overall energy to release. Here some energy is released. Say F minus, see, F minus, when you have infinite amount of water around it, it will get associated as aqueous form here. In this case, lot of energy is released here. This energy release will get added up to this one. That's why it is coming out to be greater than 13.7. Okay. This is only exception happens with fluorine. Otherwise, in all other cases, that is not going to take place. Okay. Now, let me show you. Energy released when gaseous ion is converted into aqueous ion. This energy is called as hydration energy. To understand this terminology, what is delta H of hydration? Hydration energy means how much amount of energy is released when a gaseous ion converts to an aqueous ion. For example, F minus gaseous ion is converting into an aqueous ion. Then energy released is called hydration. This we learned in chemical bonding. Okay. And that energy released is always inversely proportional to the radius of the cations or anions. Okay. And the delta H right. Next, next, let us understand one very important concept in this. That is how to find the percentage ionization of the initial acid. Okay. This is another important concept from advanced point of view. Okay. See, if you take acetic acid or any weak acid, do you think it will be 100% in an undissociated form? No, right? There will be some amount of acid which is dissociated. Okay. Let us assume like this. We'll talk in simple numbers, everybody. Imagine I have 100 acetic acid molecules. Okay. Be with me with the story. I have 100 acetic acid molecules. When I add it to water, I have realized that out of them, 5 of the acetic acid got ionized as it is. It didn't require any energy only. Okay. It didn't require any energy. Five got dissociated as its own. Probably because of the solvent, water is helping it to ionize, correct? But it got ionized. But 95 molecules of acetic acid are unionized form. Okay. They have not ionized. They remain the unionized form only. Correct. Now, when you provide the energy to break them into ions, correct? You are actually providing energy for how many number of molecules? Only 95, correct? So, experimentally, whatever the energy that was utilized, it is not utilized for all the 100 molecules of acetic acid. It is actually utilized only for 95 molecules of acetic acid. Right, everybody? But theoretically, when you write delta H of dissociation, that means how much amount of energy is required, you will assume, theoretically, you will always assume that initially I took 100 particles of acetic acid. Then to break 100 particles of acetic acid, I require some X amount of energy. Okay. But in reality, are you using the same X amount of energy or less than that? You're actually using less than that because 5 of them were already in a dissociated form, correct? Clear with the story, everybody? So, which means there are two types of dissociation energies you need to think about. One, if in the question dissociation energy is already given, which means it has to be experimental. Because if it is given means they must have done some experiment only and then gave it. So it is an experimental dissociation value. But if at all you are calculating the theoretical value from the given data, whatever you are calculating, then it has to be theoretical value. So there will always be some difference in theoretical value and practical value. Is it making sense, everybody? Okay, correct. So I'll derive this as well, just for your sake of understanding. Let me derive this as well. Suppose if you have an acid like Ha acid, right? And this is ionizing as H plus aqueous, and not 100%. It is ionizing as H plus aqueous and A minus aqueous. Okay. Let's say I took A naught moles to start with. It was undissociated first. Okay. Now out of A naught moles, some X moles have been lost. Lost means it got dissociated on its own. I didn't require any energy. Okay. Is this point clear, beta? Ah. Now, if for A naught value, suppose I require some energy, that is proportional to delta H of dissociation theoretical. This is how much you are expecting. कितना तो एनर्जी लगेगा, करेक्ट? बट एक्चुअली में इतना एनर्जी लग रहा है क्या? नहीं, एक्चुअली आप कितना एनर्जी यूटिलाइज कर रहे हो? यू आर यूटिलाइजिंग फॉर एक्चुअली ए नॉट माइनस एक्स ओनली. ओके, क्लियर बेटा? So for a naught minus x, how much amount of energy should be required? Okay, that should be delta h naught, sorry, uh, a naught minus x by a naught, correct? That multiplied by delta h naught of dissociation theoretical, correct? Guys, everybody clear on that point? So that should be equal to delta h of dissociation experimental. So experimentally this value should match actually, correct? Is the logic clear now? Very, very important logic for advance. Okay, please understand this carefully. If you have any problem, let me know. Okay. Now there is a term that we will define, which we did it in mole concept already. That is degree of dissociation. Degree of dissociation, which is alpha. Degree of dissociation is the amount that got dissociated by the initial amount. The amount which got dissociated by the initial amount. So from here I can write x is equal to a naught alpha. Let me put that value back here. So a naught minus a naught alpha by a naught into delta h of dissociation value theoretical, that should be equal to delta h of dissociation experimental. You can see the a naught value will get cancelled. If a naught value will get cancelled, so what is left here now? So that implies 1 minus alpha is equal to, you know, delta h naught of dissociation experimental divided by delta h naught of dissociation theoretical. So from here alpha will be equal to 1 minus delta h naught of dissociation experimental divided by delta h naught of dissociation theoretical. Okay, and this is what I use that as a percentage dissociation. Okay, so percentage dissociation is 1 minus delta h of dissociation practical means experimental by delta h of dissociation theoretical into 100, because I'm writing percentage dissociation. Is the proof clear, beta? Have we got that percentage dissociation? Right now, usually when you got delta h of neutralization, okay, for weak acid and C. Now this is a very important part because a lot of students make mistakes here. Check it out. If I gave you these two data, delta H of neutralization, strong acid, strong base, correct? As let's say P, I gave you this as P, okay? Minus P, like this. And delta H naught of neutralization for weak acid plus strong base as minus Q. Now delta H naught of dissociation for weak acid and, sorry, for weak acid, let this be PQR. Okay, let this be R, capital R. Now tell me, is this dissociation value which you are calculating, right? Because earlier we learned this as an formula, that is delta H of dissociation now will be equal to strong acid, strong base, this minus Q minus of minus P. That means it should be P minus Q. That is given as R. Okay. This is what we learned earlier. Okay. But my question is, what is this R? Is it theoretical or is it is experimental? R is always experimental. Why? You cannot get this value theoretically. वीक एसिड स्ट्रॉन्ग बेस के साथ कितना एनर्जी रिलीज हुआ ये तो एक्सपेरिमेंटली फाइंड करेंगे हम लोग. लॉजिक इज क्लियर. ये तो हम लोग थियोरेटिकली कुछ कैलकुलेट कर ही नहीं पाएंगे. दिस इज एन एक्सपेरिमेंटल वैल्यू. Because it is an experimental value, that means you are releasing an energy based on 95% of the acetic acid, 95 molecules of the acetic acid, not 100 molecules of acetic acid. That means this energy which is released R is actually what? It is experimental value. So remember, whenever you calculate this, so delta H of dissociation, experimental value is actually R, and delta H naught of dissociation, theoretical, has to be given in the question. It has to be given in the question. In the question, if it is given, let us say it is given as Z. It is given as Z. Then now I can write alpha, percentage alpha is equal to 1 minus experimental value is R and this value is Z, that into 100. Okay. Please go through it once. Clear? So decode the question carefully. Okay. What is given? Which one is experimental and which one is theoretical? Here it up. Right. Now let's get to the question here. What is been asked? See, if delta H of neutralization is given minus 57.3 kilojoules per mole, for weak acid strong base it is given delta H of ionization is given. So if this is given, this has to be what? Theoretical. Because you have to assume it like 100 particles are present. For that 100 particles, how much energy is required? That is theoretical. And I need to find out what is the percentage ionization. So what should be the answer? 100 into 1 minus difference of these two is experimental, which is coming as 1.2. And this is given as theoretical, which is 1.5. So percentage alpha value will be 20%. Done? Clear on that? Any doubt? Okay. See the next question. Arrange the following in the increasing order of delta T. Okay. Delta T. There are four experiments given. First one is I took 100 ml of 0.1 molar HCl. I have titrated with 100 ml of 0.1 normal NaOH. Okay. Clear beta? So total millimoles are how many? 10 millimoles. 100 into 0.1 is 10 millimoles. 100 into 0.1 is 10 millimoles. So 10 millimoles, 10 millimoles you are mixing with each other. Then let's say the energy released is Q. Let's say the energy released is Q. Then if at all have 20 millimoles and 20 millimoles, then how much energy should be released? You should be able to release 2Q. Okay. Next, if it is 100 into zero point 0.1 and 50 into zero point 0.1, then you notice that this is only 5 millimoles. These are 10 millimoles. So there is a limiting reagent here. Correct? Neutralization will only happen for the limiting amount. So for 5 millimoles only energy will be released. let's say for 5 millimoles, how much energy will be released? 0.5 Q, correct? And if it is for 200 into zero point 0.1, 100 into zero point 0.1, this is 20 millimoles, this is 10 millimoles. So again, energy release will be for limiting amount, which is Q. Okay, because 10 millimoles only it will neutralize. Okay, now that is keeping aside. If at all I need to figure out of these four, which one, because energy is released, the solution's temperature will increase. Any exothermic reaction will always increase the temperature of the system. Okay, so all these cases, temperature will be increased. Now I need to find out which case the difference in the increase in temperature is more. Now notice this. For that, the question also says that assume that the density and specific heat of the final solutions is same in all the cases. No matter whatever temperature this has gained, this has gained, this has gained, or this has gained, its heat capacity, its density is not changing. And all the solutions are in adiabatic containers. That means there is no heat loss to the surroundings. Everything is heat inside only. Okay. So if that is the case, what we can say, can I say that this Q1 will be, has to equal to, you know, uh, mass M1 into C into delta T. C is constant value here, or S, already specific heat, into delta T, correct? Similarly, Q2 has to be equal to M2 S into delta T. This I'll write it as delta T1, delta T2. Q3 has to be M3 S delta 3. And Q4 has to be M4 S delta T4. Okay. These are the heat values. Okay. So if this is a case, then what I can say, M1 into delta T1, M2 into delta T2, S is common value. Now, can I write this M1 as, volume, volume into density. So I can write this as Q1 is equal to V1 into D S delta T1. Q2 will be equal to V2 D S delta T2. Q3 will be equal to V3 D S delta T3. And Q4 will be equal to V4 into ds into delta T3. Okay. Now, if at all I take delta T1, ratio of these four, delta T1 is to delta T2 is to delta T3 is to delta T4. Now, what do we notice? We will get this as Q1 by V1 is to Q2 by V2 is to Q3 by V3 is to Q4 by V4, because D and S were common, that will get cancelled, right? So that is equal to Q is small q, right? So small q by V1. How much is the total volume here? 100 plus 100. So that is 200. That is to, this will be how much energy released in the second case? 2Q. 2Q divided by total volume is how much? 200 plus 200. So that makes it 400. That is to third case. 100 into 1, 150. So 0.5 Q by 150. And lastly, Q by 300. Q divided by 300. Okay. So you can clearly make out the Q will get cancelled, 100 will get cancelled. So what is left now? 1 by 2 is to 1 by 2 is to, how much is this one? 1 by 3 is to, clear? How much is this one? 1 by 3. Got it? Everybody understood? So from here I can say that delta T1 is same as delta T2, but it is greater than delta T3 will be same as that of delta T4. Check whether you got this or no. Very, very standard J advanced question. So easy to solve if you understand the concept, how to relate delta T in all these cases. Okay. Everyone clear? Right. Now see the next concept. This is about differential heat of solution. Differential heat of solution and integrated heat of solution. What are basic, I mean, let us understand what are these two terms represent. Okay. How are they different from the others? Correct. See, if you're talking about the enthalpy change, when 1 mole of solute is dissolved in solvent to form a solution, okay, 1 mole of solute is dissolved in any amount of solvent to form a solution, then that energy of that, I mean, the heat involved in that change is called as enthalpy of solution. Okay. For example, if I take, there are two enthalpies of solution here, by the way. One is called differential heat of enthalpy. The other one is called integral heat of enthalpy. Differential means when you have added very small amount. Okay. Clear? Oh, sorry, I wrote it the wrong way. Yeah. Integral. Yeah. Okay. Which means if at all I have a limited amount of water, it is released or required. It could be released also, or it could be required also. That is called as delta H of solution, and it is called as integral enthalpy of solution. Okay. You write it this way, or simply you write it as integral enthalpy of solution. Or here you will write it as differential enthalpy of solution. Got it? Now, in the case of differential, this is how you write down, because now you'll have large amount of water. Okay. And this is what you will notice. Got it? Usually what happens, delta, when I say differential enthalpy of solution, which means it's a constant value, because after a while, let's say after 500 ml, if you have reached to the maximum amount of energy that you can release, after that what you will notice is that furthermore there is no more energy released. Okay. So that's why graphically, if at all I write down, this is how it looks like. Okay. Now delta H value could be positive or negative. You can be plotting a positive value or negative value. So delta H value. Okay. So this is solution value, and the solution could be integral value or the differential value. That versus if I take 1 mole of sorry, this is solvent solvent amount. You can measure that in volume, or you can measure that in grams, anything like that. Okay. Then what you will notice is this is how the graph would vary like this. So if you have noticed that at one particular point here, maybe after this, you will see there isn't any change. Okay. So this is the delta H of differential form of solution. Okay. So here is that this point, what you get, this is delta H of solution, which is differential integral, differential uh, enthalpy of the solution. And because you have added some small amount here, these are all the values of different integral, different amount of integral values here, like this, like this. Okay. So this could be, when you have, let's say, less amount of volume, this is less amount of volume, so this values here are this values of delta H of solution with IES, here also delta H of solution with IES. So like this, it keeps on increasing and finally it reaches to a maximum value. Either the release energy will be positive or negative. Okay. I mean, sorry, the delta H value could be positive or negative. It could be released energy or required energy. Okay. For example, if at all I write delta H of copper sulfate converting into dot 5 H2O. If I write only dot 5 H2O, which means it is an integral enthalpy of solution, right? So delta H of hydration will be equal to delta H of solution minus delta H of solution of this. Okay. Why? Because delta H of hydrogenation, I mean delta H of solution here, sorry. Delta H of solution here is equal to, okay, this will be, how much is the delta H of solution? Sorry, this is delta H of reaction. Delta H of reaction. Delta H of reaction will be equal to how much is the delta H of solution for this one minus how much is the delta H of solution for this one. Okay, let me show you with another form here. Let's say this energy is delta H3. Now this delta H3 is the delta H of solution. This is delta H of solution of copper sulfate in a limited amount. That is when you have 5H2S. So this is integral enthalpy of solution. And if I take infinite amount of water, then I'll get delta H of solution. This is not integral. This is differential. This is differential amount. In that case, what I can say, copper sulfate dot 5H2O. Suppose if at all I take this salt and then add it to infinite amount of water, then you'll get differential form, that is delta H naught 2. So based on this graph, what can I say? That for this part, if you release some energy, that will be still lesser than this amount of energy, because this is starting from the initial amount, that is from here till here. This difference I'm talking about. Correct? Clear, beta? So this difference versus compared to that of this difference. Okay. So obviously the total copper sulfate dot 5H2O going with infinite of H2O, that should be equal to delta H3, which is this one, that is equal to delta H1 minus delta H2. Correct? So compare these three equations together. Guys, clear on that? Next enthalpies which you need to understand is about bond, enthalpies which we learned some of them, but they are most useful in Born-Haber cycle. Okay, Born-Haber cycle is basically sum of all the enthalpies to give the overall reaction enthalpy. For overall reaction enthalpy, how much amount of energies, how many different types of enthalpies which are involved. Okay, the sum of all those enthalpies is what we are trying to calculate. Clear? Right. So check it out. Na plus Cl minus. Sorry, first let us understand what is lattice energy. Should be useful here. Energy released when two ions of oppositely charged species approach each other from infinite distance. This we discussed in chemical bonding already. Let's say this is an positive charge, negative charge approaching from infinite distance to form 1 mole of a crystal solid. Okay, so crystal solid, that would be equal to delta H of U. Delta H of U means lattice. Okay. Now notice Na2O solid, correct? If you take Na2O solid formation. Now, how do we get the formation reaction? See, formation reaction will be from sodium solid plus half of O2 giving Na2O, correct? Now the amount of energy that is released or required is what we call it as delta H of formation of Na2O. How do I get this using this, using this forms here? Let's see. Sodium in a solid state, if it has to convert into gaseous state, then sublimation is required. So you can see 2 moles of sublimation is required. Then 2 moles of sodium to convert into ions. I require 2 moles of ionization. I mean 2 times of ionization. For that means for 2 moles, I require 2 times of the ionization energy. Now I got Na plus ions. O2 also I want to make it into an ionic form. So first delta H of dissociation, that will convert into half of, sorry, half of delta H of dissociation. So that will convert into oxygen atom. And for oxygen atom to convert into O2 minus, I need to make 2 electron affinities. So these are 2 electron affinities, or I can also write it as delta H of electron gain enthalpies. And once you get the ions in the gaseous state, that's what I have defined lattice energy. Remember, these 2 lattice energies will form 1 mole of solid crystal. So therefore, combining these two, the energy will be released, and that release energy is called lattice energy. Clear, guys? So check out delta H of formation. Formation will be equal to, you know, 2 times of sublimation energy plus 2 times of ionization energy plus delta H of dissociation energy. Half of, sorry, half of delta H of dissociation energy. Okay, 1 second. Check. So this is equal to half of delta H of dissociation plus electron affinity 1 and 2. This is electron affinity 1 and 2. And lastly, we are adding lattice energy. So adding all of this, then the energy released or energy required is called as delta H of formation. Clear, everybody? Now here what you need to understand is one thing, which of them are being positive and which of them are being negative. So this is positive value, positive value, positive value. Lattice energy is negative value. Now this is positive value if you write it in electron affinity, but it is negative value if you write it in electron gain enthalpy. You know that electron gain enthalpy is opposite of it. So I'll write down the both of the forms. Delta H of formation is equal to 2 times of delta H naught of sublimation plus 2 times of ionization energy plus half of delta H naught of dissociation. Clear? Plus, you know, delta H of electron gain enthalpy 1 plus delta H of electron gain enthalpy 2, that plus delta H of lattice. These are all the energies which are involved, out of which this is positive, 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 this is negative, negative, and negative. So after making all the sum, this might come as positive or this might come as negative. Clear, everybody? Right. Now, using the same concept, correct? Using the same concept, clear? I want you to make a Born-Haber cycle. Take some time, use the same Born-Haber cycle. Make the Born-Haber cycle now for, you know, Born-Haber cycle, delta H of formation of Al2O3 solid. Make Born-Haber cycle for this one, everybody. Delta H of formation of Al2O3. Okay. I'll give you 5 minutes, everybody. So please try that and then I'll discuss. Clear? Right. Let's see whether you got this part. So you got to start with 2 moles of Al solid plus 3 by 2 moles of O2 gas. That to prepare Al2O3 solid. Got it? And for that, 2 moles of aluminum will be first converted into 2 moles of Al gas, and from there you have to convert that into 2 moles of Al plus 3 gas, and here you need to convert this into 3 by 2, sorry, 3 moles. 3 moles of oxygen gas, that I need to convert into 3 moles of O2 minus gaseous ions. Then combining these two, I should be able to get this product. So now let me write down what are all the enthalpies. Delta H naught of sublimation into 2. This is, ion 2 times of IE1 plus IE2 plus IE3, ionization 3. Okay. While here it is 3 by 2 times of epsilon O double bond O, or you can write it as bond dissociation enthalpy. And here I'll require 3 times of, okay, electron affinity 1 plus electron affinity 2. Electron affinity 2. Okay, clear? Now here I made one mistake. You guys need notice. Do you remember electron gain enthalpy of the second one will always be positive? You can never get a, because only for the first electron you might get a negative value, but for second electron, for any species, if you add, it will always get a positive value. Okay, so keep that in mind. The second one has to be positive. So now here the amount of energy that is released in this case will be the lattice energy. Okay, so this will be the lattice energy U. So now if I write this as delta H of formation, that has to be equal to 2 times of delta H naught of sublimation plus 2 times of ionization 1, ionization 2, ionization 3, all of them being positive values, plus 3 by 2 times of delta H of dissociation value plus 3 times of EA1 plus 3 times of EA2, and that plus delta H of lattice. Now you notice that this is positive value. All these three are positive values. This is positive value. The first one is positive value, but the second one is negative value, because now I'm writing in electron affinity. But if I write it in electron gain enthalpy, the first one is negative, second one is positive, and the last one is negative. This is the released energies. Done. JEE advanced question will be framed based on one of the component missing in it, and you're supposed to find. Rest of the values will be given. Okay, that's a very standard question you will get. Everybody understood how to use the Born-Haber cycle, right? Now, before going into Kirchhoff's law, there is one term which we need to understand, which is enthalpy of solution. Enthalpy of solution, okay, for ionic compound. Enthalpy of solution for ionic compound. Just like how we write the lattice energy, which is also from ionic compound, here we are writing enthalpy of solution for ionic compound. That means just like we got a formation of a compound, let's say this is a formation of a solid ionic compound. As soon as you add it to infinite amount of water, correct? So this salt should get dissolved, and if it is gaining into an aqueous ion like this, plus y in aqueous form plus y times of B minus x in aqueous form, then we know that this is called as delta H of solution. This is called as delta H of solution. And here I can write it in two forms here. First, if I write this in a reverse way, that is, consider this is becoming x moles of A plus y plus y moles of B minus x, both in gaseous state. So I am taking this many number of ions to combine and get 1 mole of solid. Then the reverse is delta H of lattice only, right? So it is a reverse of lattice energy. Clear? This is a reverse of lattice energy. So this is the lattice energy of AX BY solid. And now from here, if this one is to be converted into aqueous ion, or this one need to be converted into an aqueous ion, then the energy required is called as hydration energy. So for 1 mole, if it is for x moles, I'll write it as x times of delta H of hydration energy of positive values of positive charge. Here y times of delta H of hydration of the anions. One is for cation, one is for anion. Thus, delta H of solution total has to be equal to delta H of lattice of AX BY in solid state plus x times of delta H naught of hydration for cation plus y times of delta H of hydration for anions. Done. So this is the formula that will be directly useful whenever you need to calculate delta H of solution, hydration or enthalpy, whatever is unknown given. Usually, what you would notice, usually you will notice that if the magnitude of delta H of hydration, which is a of total of delta H naught of positive, sorry, delta H of hydration of positive value of cations plus delta H of hydration of anions. This total, right? If this is the total value, then I can say if delta H of hydration is dominant than delta H naught of lattice, right? Then salt or ionic solid, in this case salt or that ionic solid, will be completely soluble. Completely soluble. That means it get completely dissolved. Delta H naught of hydration, if it is equal to delta H naught of lattice, then ionic compound, then ionic solid get dissolved, dissolved and reach maximum solubility. This is the maximum solubility of the salt or the solid ionic compound. And if delta H naught of hydration is less than delta H of lattice, then we call it as ionic compound is sparingly soluble, or ionic solid is sparingly soluble. So it is not completely soluble. It is very small amount of solubility is observed. Got it? For instance, if I take something like, do you remember any salt like, let's say some Disprin tablet or a Eno, you know, right? Those Eno powders, correct? Carbonate powders. So when you add it to water, what will happen? Immediately they'll, release the energy and they'll start dissolving, correct? They'll all get dissolved. So here their hydration is dominating their lattice. That's why they are getting easily dissolved and overall energy is released. That's why you will see slightly some, the liquid will start slightly heating up. Second case, if the hydration and lattice are very close to each other, that's what happens with common salt. Common salt, the values are very close to lattice and hydration values are very close to each other. And now, if that is the case, then you might still see dissolution. See, when you add common salt to water, you will not see sudden dissolution. You will have to add some convectional force. You have to put some spoon and, move it around, correct? That is convection. So you have to give some convectional force so that it get completely dissolved. Yeah. Lastly, if you have, sparingly soluble salts, like let's say chalk piece for instance, if you take chalk piece powder and add it to water and mix it, no matter how much you mix it, very small amount will get dissolved. Why? Its lattice energy is much more stronger than its hydration energy. You know, I hope all of you understood what is enthalpy of solution for ionic compounds. Done, beta? Yes. Okay. Most of the enthalpies are covered here. Now this is an application, which is Kirchhoff's law, a very simple application. After that, we'll start with the next part, which is entropy. Clear? So next class, we'll start off with entropy. Got it? That will be about second law of thermodynamics. Now, since we got enough terms to understand from enthalpy's point of view, now in the second law, whatever terms I'll be using, you'll be able to recall them from thermochemistry. Clear? So I suggest, one second.